Thanks for joining me today for this session, which is about processing streaming data with AWS Lambda. My name is James Bezic, and I'm a principal developer advocate here in the AWS serverless team. I'm a self-confessed serverless geek, and I've built quite a few production systems using serverless infrastructure. Prior to being a DA, I was a software developer for many years and also a product manager for a long time. The most important thing on the slide here is my Twitter handle and my email address. So if you have any questions about Kinesis or serverless in general, feel free to reach out to me and I'll do my very best to help. Today we're talking about processing streaming data with AWS Lambda. In this session, I'll cover 5 topics. First, I'll talk about streaming use cases and briefly explain the different Kinesis services. Then I'll show how you can build zero administration stream processing with Kinesis Data Firehose. Lambda is a really important service for processing streaming data, so I'll talk about how to use it for on-demand compute with Kinesis data streams. In production systems, it's important to know how to scale, monitor, and troubleshoot Kinesis, so I'll provide some important guidance here. And finally, I'll discuss how to optimize your Kinesis-based application and highlight some best practices. Amazon Kinesis makes it easier to collect, process, and analyze real-time streaming data. For applications, this can help you get timely insights and react quickly to new information. Kinesis provides cost-effective streaming data processing at any scale, with the flexibility to choose the tools that best suit the needs of your workload. Moving from traditional batch architectures to streaming architectures, it creates new capabilities. You go from hourly server logs to real-time metrics, or from weekly and monthly bills created by a job to a system that monitors real-time spending alerts and implementing spending caps. In analyzing click streams, it can move from daily reports to a real-time analysis. And for customers like financial institutions who have fraud detection systems, critically, this information can drive real-time detection. Bringing real-time capabilities to workloads fundamentally changes the capabilities and the problems that you can solve. There are a wide variety of use cases for Kinesis. Here are just a few of the common ones that we see from our customers. In video processing, Kinesis allows you to stream video from connected devices to AWS for analytics or machine learning. The video can then be processed by other services depending upon the needs of the workload. In industrial automation, sensors collect large amounts of data from thousands of devices. This data can be ingested by Kinesis and analyzed by Kinesis Data Analytics in real time to power dashboards for real-time monitoring. The data can also be stored and analyzed historically or used to train machine learning models. You can use Kinesis to process streaming data from IoT devices such as consumer appliances, embedded sensors, and TV set-top boxes. You can then use the data to send real-time alerts or take actions programmatically when a sensor exceeds certain operating thresholds. Data connected via Kinesis can also be filtered and aggregated with Kinesis Data Firehose and then stored durably in S3 buckets to create data lakes. This enables analytics and machine learning for use cases like production optimization and predictive maintenance. Kinesis data streams can be used to collect log and event data from sources such as servers, desktops, and mobile devices. You can then build Kinesis applications to continuously process the data, generate metrics, power live dashboards, and emit aggregated data into stores such as Amazon S3. Under the Kinesis umbrella, there are 4 distinct services with different capabilities. Kinesis Data Streams is a highly scalable and durable real-time data streaming service that can continuously capture gigabytes of data per second from hundreds of thousands of sources. Amazon Kinesis Video Streams makes it easy to securely stream video from connected devices to AWS for analytics, machine learning, and other processing. I'm not covering this service today, but it's an important part of the Kinesis suite. Kinesis Data Firehose is a managed streaming service with minimal administration, and it's the easiest way to capture, transform, and load data streams into AWS data stores. You can use the data collected here for real-time analytics with existing business intelligence tools. Kinesis Data Analytics enables you to process data streams in real time with SQL or Apache Flink. You can use familiar programming languages like SQL to build complex queries that run continuously on streaming data. Generally, this is the pattern for implementing a streaming data solution. Data producers continuously generate data and write it to a stream. A data producer could be a web server sending logs, or it could be an application server sending metrics, or it could be an Internet of Things device sending telemetry. The streaming service then durably stores the data once it's been received. It provides a temporary buffer to prepare the data, and it's capable of handling high throughput. The streaming service delivers the records to data consumers. The consumer continuously processes the data. In many cases, this means cleaning, preparing, and aggregating the records, transforming the raw data into information. Producers create records, and records contain 3 pieces of information. The partition key logically separates sets of data, and it's hashed to route the data to a shard. The sequence number is unique per partition key within the shard. It's assigned by Kinesis after the producer writes to the stream. And the data blob is a base 64 encoded payload up to 1 megabyte in size. Using Kinesis enables you to decouple the data producer and consumer, which can help promote the development of a microservices model and make it easier to manage large workloads. Producers put records into streams, and consumers get records from streams and then process them. The delay between the time a record is put into the stream and the time it can be retrieved, this is called the put to get delay, is typically less than 1 second. So a Kinesis data streams application can start consuming the data from the stream almost immediately after the data is added. A Kinesis data stream is a set of 1 or more shards. Each shard contains a sequence of data records, and each data record has a sequence number that's assigned by the service. If your data rate increases, you can increase or decrease the number of shards allocated to your stream. Kinesis can automatically encrypt sensitive information as a producer enters it into the stream. It uses AWS KMS for encryption. Record ordering is maintained within each shard, and you can configure record retention for up to 1 year. A shard is a uniquely identified sequence of data records in a stream. It provides a fixed unit of capacity. Each shard can support up to 1,000 records per second for writes, up to a maximum total data write rate of 1 megabyte per second, including partition keys. Each shard can support up to 5 transactions per second for reads, up to a maximum total data read rate of 2 megabytes per second. The data capacity of your entire stream is a function of the number of shards that you specify for the stream, and the total capacity of the stream is the sum of the capacities of the shards. Each shard contains records ordered by arrival time. In a shard, records from the trim horizon are all the available records since the beginning, whereas records from the tip or the latest are the most current records. Essentially, the difference is whether you want to start from the oldest record, the trim horizon, or from right now, the latest, and skip data between the latest checkpoint and now. Lambda is the on-demand compute service at the heart of the AWS serverless portfolio, and it can consume and process data from Kinesis streams. The Lambda service polls Kinesis automatically and invokes your Lambda functions when records are available. The benefit of using Lambda for streaming data processing is that Lambda manages scaling, and that allows you to focus on the custom business logic to process data instead of the underlying infrastructure. Records are delivered as a payload to the Lambda function, and you can configure how many records are in each batch, up to 10,000, or 6 megabytes as a total payload limit. Lambda supports a variety of custom runtimes natively, such as Python, Node, and .NET, and you can also bring your own runtime too. We have customers running even Erlang, PHP, or COBOL. Lambda is agnostic to your choice of runtime. In the event source mapping, you can also configure a starting position for records. You can process only new records, all existing records, or records created after a certain date. Once a Lambda function is finished processing, it returns the result to Kinesis. For each shard, Lambda configures a poller that polls the shard every second and invokes your Lambda function when records are available. The poller is managed internally by the Lambda service. Internally, a record processor polls the Kinesis shard. The batcher creates the batches to be processed by the function, and the invoker gets batches and invokes your Lambda function. Kinesis Data Firehose is a fully managed service that automatically provisions, manages, and scales the resources required to process and load your streaming data. You configure Data Firehose within minutes in the console, CLI, or CloudFormation, and it's then immediately available to receive data from thousands of data sources. Firehose can optionally invoke a Lambda function to transform data before it stores results. It's integrated with some AWS services like S3, Redshift, and the Elasticsearch service. It can also deliver data to generic HTTP endpoints and directly to service providers. From the console, you point Data Firehose to the destinations you need and use your existing applications and tools to analyze streaming data. Once set up, Data Firehose loads streaming data into your destination continuously as they arrive, and there's no ongoing administration, and you don't need to manage shards. It's also a pay-as-you-go service where the cost is based upon usage with no minimum fees. There are various sources for Data Firehose. The first is a direct put from the data producer. You can send data using the Kinesis agent, the Data Firehose API, or the AWS SDK. You can also configure your Data Firehose delivery stream to automatically read data from an existing Kinesis data stream. And you can use CloudWatch logs, EventBridge, or IoT as a source. Apart from S3, Redshift, and Elasticsearch, there's also a range of partners that you can use as destinations for Data Firehose. These include Datadog, Dynatrace, Logic Monitor, MongoDB Cloud, New Relic, Splunk, and Sumo Logic. For HTTP endpoint delivery, there is a defined request and response format. Endpoints have 3 minutes to respond to a request before a timeout occurs. The frequency of data delivery to S3 is determined by the buffer size and buffer interval values that you configure for your delivery stream. The service buffers incoming data before delivering it to S3. You can configure the buffer size between 1 to 128 megabytes or buffer interval between 60 and 900 seconds. The condition that is satisfied first will then trigger data delivery to S3. When data delivery falls behind data writing to a stream, the service raises the buffer size dynamically. This allows it to catch up and ensure that the data is delivered to the destination. Firehose also buffers incoming data before delivering it to Splunk. The buffer size is 5 megabytes and the buffer interval is 60 seconds. These aren't configurable because they're optimized specifically for the Splunk integration. The overall operation of a Data Firehose stream looks like this. The data source puts records onto the stream. Firehose invokes the data transformation Lambda function to process the records. It uses the batch size value in the configuration to determine the number of records sent per invocation. The transformed records are returned from Lambda back to the Firehose stream. Those records are then forwarded to the destination, in this case, the Amazon Elasticsearch service. If your Lambda function invocation fails because of a network timeout or because you've reached the Lambda invocation limit, Firehose retries the invocation 3 times by default. If the invocation does not succeed, Firehose then skips that batch of records. Any skipped records are treated as unsuccessfully processed records. If the status of a data transformation of a record is processing failed, then Firehose also treats the record as unsuccessfully processed. Any unsuccessfully processed records are delivered to your S3 bucket in a folder called processing-failed. This will include metadata indicating the number of attempts made, the timestamp for the last attempt, and the Lambda function's ARM. Firehose can back up all untransformed records to your S3 bucket concurrently while delivering transformed records to your destination. You can enable source record backup when you create or update a delivery stream. When you enable data transformation, the service buffers incoming data by up to 3 megabytes by default. You can adjust this buffering size by using the Processing Configuration API. Firehose then invokes the specified Lambda function asynchronously with each buffered batch using the Lambda synchronous invocation mode. The Lambda function processes and returns a list of transformed records with a status of each record. The status is an attribute called result with the possible values of OK, dropped, or processing failed. In the returned payload, the data attribute must be base64 encoded. The transformed data is then sent back from Lambda to Firehose, and from there, it's sent to the destination once the specified buffering size or buffering interval is reached, whichever one happens first. The data transformation Lambda function can run for up to 5 minutes. These functions are commonly used to filter, enrich, and convert data. In filtering, the Lambda function can remove attributes from records or remove entire records based upon your business logic. Some customers use filtering to remove personally identifiable information from records and streams, for example. You can also enrich records by fetching data from other AWS services or from external data sources. One common process is to use a GeoIP service to look up the geographical location of IP addresses and append this data to records. Just remember that the response size in asynchronously invoked Lambda functions is 6 megabytes. In converting data, you have complete flexibility in modifying the record layout to match the needs of your data consumer. There are Lambda blueprints available as examples of data conversion using this process. Firehose passes a record ID along with each record to Lambda during the invocation. Each transformed record must be returned with the exact same record ID. Firehose invokes the data transformation Lambda function and scales up the function if the number of records in the stream grows. When the destination is S3, Redshift, or the Elasticsearch service, Firehose allows up to 5 outstanding Lambda invocations per shard. When the destination is Splunk, the quota is 10 outstanding Lambda invocations per shard. You can monitor a data Firehose stream in several ways. Firehose sends Amazon CloudWatch custom metrics and logs with detailed monitoring for each delivery stream. If you're using the Kinesis agent, this also publishes custom CloudWatch metrics to help assess whether the agent is working as expected. The service also uses CloudTrail to log API calls and store the data in an S3 bucket to maintain an API call history. To monitor data transformations, watch an alarm on the execute process.success metric for the delivery stream. Check the ratio of successful Lambda functions to all Lambda functions. This should be nearly 100% constantly, and if it's not, check the Lambda functions logs to investigate further. And watch an alarm on the delivery to star.success metric. Similarly, these should also be nearly 100% all of the time. Next, let's take a look at Amazon Kinesis data streams, which is a massively scalable and durable real-time data streaming service, and how it's used with Lambda. Data streams makes your streaming data available to multiple real-time analytics applications within about a second of the data being collected. Producers send data to streams, and you can use up to 5 consumers to process records. If you use Kinesis Data Analytics or Data Firehose on a stream, these count towards this subscriber limit. Lambda is one type of consumer you can use to process data from a stream. The Lambda service polls each shard in your Kinesis stream for records. The event source mapping shares read throughput with other consumers of the shard. Lambda reads records in batches from the data stream and invokes your function synchronously. The batch of records is delivered in an event payload. So let's look at shard processing. The Lambda service polls the shard once per second for a set of Lambda records, and then synchronously invokes the function with a batch of records. If the processing is successful, it moves on to the next batch. If not, the retry and error behavior will depend upon the event source configuration. Using the default settings, Lambda invokes the function again with the same batch of records. It continues to do this until the batch is successful or the records expire out of the stream. This may not be ideal for large batches, so you can also use the bisect batch on function error feature. In a batch processing failure, this will often be caused by a single record, and this feature helps find that record. Using this, Lambda splits the batch into two, retrying the oldest half of the records first. This splitting process is repeated recursively until it finds the one record that's causing the failure. The other batches process successfully. The batch with one record is retried until successful, respecting the maximum number of retries and record age in the stream. In this case, earlier retries do not count towards the maximum retries. For records that are retried, the maximum number of times, or they've aged out of a stream, those will be discarded. Oftentimes, you will want to save these messages. So to do this, configure a failure destination, and instead, those records will be sent there. You can scale the throughput of Kinesis data streams by adding shards to a stream. The easiest way to do this is with the Update Shard Count API. To use this, set a target shard count, and the API will manage splitting and merging shards in the background. This process is asynchronous, and it can cause short-lived shards to be created in addition to the final shards. The short-lived shards count towards the total limit for your account in the region. When using this API call, we recommend that you specify a target shard count that is a multiple of 25%. So 25%, 50%, 75%, and so on. You can specify any target value within your shard limit. However, if you specify a target that isn't a multiple of 25%, the scaling action might take longer to complete. For advanced users, you can use split shard and merge shard directly. This is an example of the CLI command to scale a stream from 4 to 6 shards. If the action is successful, the service returns a 200 response with a JSON payload containing the stream name, current shard count, and the target shard count. This process is asynchronous, so the response occurs before the scaling operation is complete. Using this API, there are some important limits. You cannot scale to more than 10 times per rolling 24-hour period per stream. You cannot scale up to more than double your current shard count for a stream. You cannot scale down to below half your current shard count for a stream. You also cannot scale to more than 10,000 shards in a stream, or if your stream already has more than 10,000, scale down unless the target is under 10,000. Many of these quotas in place are soft limits, so contact AWS support if you need higher limits. Resharding enables you to increase or decrease the number of shards in a stream to adapt to changes in the rate of data flowing through the stream. It's typically performed by an administrator or monitoring application in response to Kinesis metrics. You must specify the new starting hash value when performing this command. This value determines the point of the split within the parent shard hash key space. In most cases, you want to do an even split. After issuing the API call, the existing stream goes into updating status, and the stream scales up by splitting shards. This creates two new child shards that split the partition key space of the parent shard. The parent shard is still available, but it enters a state called closed. The consuming Lambda function does not start receiving records from the child shards until it's processed all the records from the parent shards. Once the last records are processed in the parent shard, its status becomes expired, and no more records will be processed by that shard. Whereas only one Lambda function processed the shard before splitting, once the child shards are open and active, now there are two Lambda functions. Kinesis data streams and CloudWatch are integrated. The metrics that you configure for your streams are automatically collected and pushed to CloudWatch every minute. There are several useful metrics to monitor your streams and shards. The getRecords.IteratorAge milliseconds metric measures the difference between the age of the last record consumed and the latest record put to a stream. This is important to monitor, since having too high of an iterator age in relation to your stream's retention period can cause you to lose data as records expire from the stream. This value should generally not exceed 50% of your stream retention. When you get to 100% of your stream retention, data will be lost. If you're getting behind, a temporary stopgap is to increase the retention time of your stream. The better solution is to add more consumers to keep up. When your consumers exceed the ReadProvisionedThroughputExceeded metric, they will start being throttled and you won't be able to read from the stream. This can start backing up your stream. So monitor the average statistic for this metric and try to get this value as close to 0 as possible. The same is true with the WriteProvisionedThroughputExceeded metric. When exceeded, producers are throttled and you won't be able to put records to the stream. Monitoring the average for this statistic can help you determine if your producers are healthy. The putRecord.success and putRecords.success metrics are incremented whenever producers succeed in sending data to your stream. Monitoring for spikes or drops can help you monitor the health of producers and catch problems early. You'll want to watch the average statistic for whichever of the two API calls you're using, because CloudWatch splits the two APIs into two different metrics. GetRecords.success is the consumer-side equivalent of putRecords.success. Look for spikes or drops in this metric to ensure that your consumers are healthy. The average is the most useful statistic for this purpose. There are also several useful metrics for monitoring Lambda function consumers. Set alarms on errors and throttles when these go over 0, so you can investigate further. Also monitor spikes in duration, which may indicate if the consumer is slowing down, so you can take corrective action. Lambda emits the IteratorAge metric when the function finishes processing a batch of records. The metric indicates how old the last function in the batch was when the processing finishes. If your function is processing new events, you can use the IteratorAge to estimate the latency between when a record is added and when the function processes it. If the IteratorAge starts to grow rapidly, here are some troubleshooting steps and questions that can help alleviate the problem. How many Lambda functions are subscribed to the stream? Can you add another consumer to help process records? Are any functions showing errors or throttles in their metrics? Are you seeing a large increase in the incoming records or incoming bytes metrics in the stream that indicate a growth in producer data? Instead of allowing a function to error out, you could use try-catch handling to log the records that cause the errors and then return successfully. This allows Lambda to process the next batch. You can also scale the Lambda concurrency per shard by using the parallelization factor, which I'll discuss in a few minutes. Increasing Lambda memory can also increase the performance of Lambda consumers, since it increases the amount of virtual CPU and compute power available for processing. The ReadProvisionedThroughputExceeded metric can warn you when you're reaching the 5 reads per second or 2 megabytes per second limit. If you can remove subscribers, this can alleviate the issue. Remember that Kinesis Data Analytics and Kinesis Firehose are also subscribers, so you can remove these if they're not needed. If you need all the subscribers on the stream, one way to solve this is to use enhanced fanout. This feature enables consumers to receive records from a stream with a throughput of up to 2 megabytes of data per second per shard. This throughput is dedicated, which means that consumers using enhanced fanout don't contend with other consumers that are receiving data from the stream. Kinesis pushes data records from the stream to consumers using enhanced fanout, meaning these consumers don't need to poll for data. To see how this works with Lambda consumers, see the compute blog post at s12d.com/enhanced fanout. In this next section, I'll talk about some features and configurations available for optimizing the performance of your Kinesis data streams application. Lambda consumers can use enhanced fanout and HTTP2. To minimize latency and maximize read throughput, you can create a data stream consumer with enhanced fanout. Stream consumers can get a dedicated connection to each shard that doesn't impact other applications reading from the stream. The dedicated throughput can help if you have many applications reading the same data, or if you're reprocessing a stream with large records. Kinesis pushes records to Lambda over HTTP2, which increases performance by up to 65%. Standard consumers use a pull model over HTTP, whereas EFO consumers use a push model over HTTP2. A standard consumer with 5 consumers would average 200 milliseconds of latency each. It's up to 1 second for all 5. Using enhanced fanout, the consumers are completely independent and do not impact each other. Even with 5 consumers, each consumer averages about 70 milliseconds of latency. The read throughput is dedicated, so this provides significantly faster throughput for many workloads. But note there is an additional charge for using this feature. By default, there is 1 instance of a Lambda function per shard in a stream. You can increase the number of concurrent Lambda functions that are processing a shard by changing the parallelization factor. The batches maintain in-order processing per partition key, and this feature is available for both Kinesis data streams and for DynamoDB streams. Changing the parallelization factor from 1 to 2, you can see in this diagram how each shard now has 2 instances of a consuming Lambda function processing batches in parallel. The result is that records are processed in half the time, all things being equal. You can also increase this value to a maximum of 10. Kinesis has a per shard write limit of 1 megabyte per second, or 1,000 messages a second. If your data producers are creating many small messages, you may reach the limit of messages while still being under the 1 megabyte per second limit. Having many small messages can lead to lower throughput per shard, and it can increase the cost of a workload. You can often resolve this issue by using aggregation to increase the payload size, reduce the number of messages, and improve the throughput. There are 2 libraries commonly used to help with this: the Kinesis Producer Library, KPL, and the Kinesis Aggregation Library. The KPL provides a layer of abstraction for ingesting data, and it offers a synchronous and asynchronous interface. It's recommended to use the asynchronous interface wherever possible. The KPL handles batching and multi-threading, and it also emits metrics to CloudWatch so you can monitor performance. For Java users, the Kinesis client library integrates seamlessly with the KPL and can help on the consumer side. Otherwise, for consumers using other runtimes, the Kinesis aggregation library can help simplify the de-aggregation process if you use this technique. For streams with low numbers of records, you may find that the consuming Lambda function is invoked with small batches, which increases the processing cost per message. If the latency sensitivity of the workload is less important, for example, in archiving workloads, you can change this behavior to wait for more messages to arrive before invoking the Lambda function. By default, Lambda invokes your function as soon as records are available in the stream. If the batch that Lambda reads from the stream has only 1 record in it, Lambda sends only 1 record to the function. To avoid this, you can tell the event source to buffer records for up to 5 minutes by configuring a batch window. Before invoking the function, Lambda continues to read records from the stream until it's gathered a full batch, or until the batch window expires. This is an additional knob to tune the streaming trigger. You can set a time to wait before triggering, up to 5 minutes, set in seconds. The batch size is still respected, and it will trigger on full batches before the batch window is up. This works for both Kinesis data streams and DynamoDB streams triggers. Kinesis Data Analytics is the easiest way to transform and analyze streaming data in real time. You can interactively query streaming data using standard SQL, and you can build Apache Flink applications using Java, Python, and Scala. You can also build Apache Beam applications using Java to analyze data streams. You can use Kinesis data analytics for many use cases to process data continuously and derive insights in near real time. There are three common use cases for Kinesis data analytics. Streaming ETL. You can prepare data before loading into a data lake or data warehouse, normalizing data with a specified schema and reducing or eliminating batch ETL steps. For continuous metric generation, KDA calculates statistics and trends over time. You can use this to create real-time leaderboards in games or measure sensor averages in IoT devices over a rolling time window. Finally, for responsive real-time metrics, you send real-time alarms or notifications when certain metrics reach predefined thresholds or when your application detects anomalies. In all cases, the process is the same. You initially capture data via Kinesis Data Firehose or Kinesis data streams, and then Kinesis Data Analytics is the consumer for those streams. The output is then sent to downstream consumers and tools for alerting, visualization, and distribution. Kinesis Data Analytics implements the ANSI 2008 SQL standard with extensions. These extensions enable you to process streaming data using SQL. If you're building a SQL application, there are a couple of important concepts that I want to briefly introduce. The first is a stream. You map a streaming source to an in-application stream that is created using a SQL statement like this. Data continuously flows from the streaming source into the in-application stream. This stream works like a table that you can query using SQL statements, but it's called a stream because it represents continuous data flow. You can have multiple writers insert data into an in-application stream, and there can be multiple readers selecting from the stream. Think of this as an in-application stream that implements a publish-subscribe messaging paradigm. In this paradigm, data can be processed, interpreted, and forwarded by a cascade of streaming SQL statements without having to be stored in a traditional relational database. Once you've created an in-application stream, then you can pump data into it using a pump, which is defined using a statement like this. A pump is a continuous insert query that's running to insert data from an in-application stream into another in-application stream. SQL queries in your application code execute continuously over in-application streams. These streams represent unbounded data that flows continuously through your application. To get results from this continuously updating input, you bound queries using a window defined in terms of time. These are also called windowed SQL. For a time-based windowed query, you specify a time-based windowed size. You can specify a query to process records in a tumbling window, a sliding window, or a stagger window, depending on your application. Sliding windows aggregate data continuously using a fixed time or a row count interval. Tumbling windows aggregate data using distinct time-based windows. These open and close at regular intervals, such as every 15 minutes. Stagger windows use keyed time-based windows. These windows open as data arrives, and the keys allow for multiple overlapping windows. If you need to use tumbling windows in your aggregations, there's a relatively new feature that can help. Lambda now supports streaming analytics calculations for Kinesis. This allows developers to calculate aggregates in near real time and pass the state across multiple Lambda invocations. This provides an alternative way to build analytics solutions. A tumbling window in Lambda is a fixed size, non-overlapping time interval of up to 15 minutes. You specify the duration in the event source mapping between the stream and the Lambda function. When you apply a tumbling window to a stream, items in the stream are grouped by window and sent to the processing Lambda function. The function returns a state value that is passed to the next tumbling window. In the diagram shown, a stream has 4 windows over 60 minutes. The first window contains items 1 and 5. The function sums these and returns the value 6. The sum result is passed to the second tumbling window, which adds 3, 2, and 7. That brings the total to 18, and that's passed to the third window, and so on. In practice, tumbling windows in Lambda look like this. The incoming event is the same as before. Kinesis provides an array of records. What's different is the handful of new attributes. There's a start and end time to the window and a state attribute. The state is initially empty. The first invocation returns a value in the state, in this case, the item count and sales total. When Kinesis invokes the second Lambda function, it passes the state it received from the first. When the final invocation occurs, there is a new attribute in the event payload indicating that it's the last one. You can then choose to durably persist the calculation result in S3, DynamoDB, EFS, or another downstream service. When you're building data streaming solutions that use Lambda consumers, you can do everything in the AWS Management Console. But once you get familiar with building these applications, it's often easier to move to an infrastructure as code solution. The AWS Serverless Application Model, also known as SAM, lets you express the Lambda function and the event source mapping in code templates. Using the SAM CLI, you can then deploy these templates into your AWS account. These can help create repeatable, versionable deployments that you can share across teams. Here's an example of a SAM template that deploys a Kinesis data stream, a consumer, a Lambda function, and the IAM resources needed to run the application. You can see and deploy the entire example in the URL shown on the slide. The first resource is the Kinesis stream itself, which is defined with a shard count of 1. The next resource defines the Kinesis stream consumer. It sets the stream ARN, that's the Amazon resource name, and the consumer name. Next, the template defines the Lambda function to consume the records from the Kinesis stream. The SAM template specifies the code location, runtime, and handler name. The event source mapping references the application consumer for the Kinesis stream. It sets the starting position to latest. It could have used the trim horizon instead, and a batch size of 100 records. The batch size specifies the number of records that the Polars batcher gathers before it invokes the function. Finally, the output section of the template provides references to the resources that have been created. This entire SAM template can be deployed from the command line using the SAM CLI. We've reviewed some of the capabilities of the Kinesis suite of services. I want to leave you with a few general best practices that can help you operate production streaming workloads. It's important to understand the choice between Kinesis Data Firehose and Kinesis Data Streams. Firehose is a fully managed and scalable service that requires no administration, so if your streaming workload is storing data in one of its targets, like S3 or Redshift, this is often the best choice. Data Streams provides more flexibility, but you must monitor the shard activity and understand how to scale up and down as needed. Architects frequently advise customers to design their streaming applications with your data consumers in mind. You may have a variety of different types of consumer with different needs, and working backwards from their requirements can help you build a solution that provides the most value. If the payload received by Lambda functions, then you may receive data blobs with inconsistent data structures and varying attributes. Generally, it's best to transform this raw data into aggregation-friendly records that downstream consumers can work with more easily. Before getting to production, we recommend becoming familiar with the mechanisms for monitoring and scaling streams ahead of time. You can build CloudWatch dashboards containing many of the important metrics to monitor performance, so you're ready before going into production. Similarly, understanding the troubleshooting steps to tackle common streaming issues can also save significant time, and I covered a few of those common ones earlier. For more information, head over to serverlessland.com, where there are more resources, blogs, videos, workshops, and learning paths to help you learn more about developing serverless solutions on AWS. My name is James Bezic, and I'm a Principal Developer Advocate here in the AWS Serverless team. If you have any questions at all about streaming data or serverless technology in general, feel free to contact me. Thanks very much for your time today.